So let's start with a couple of things. Find, thank you, the Maclaurin series for x squared e to the x cubed. Now, there's a couple ways we could do this, but the sensible way to do it is to use a known Maclaurin series and then modify it. So you could start taking derivatives, doing all that crazy stuff, but as you can see, derivatives of this after like the first couple times are going to get way out of hand. Product rule, chain rule, all that stuff. So instead, we're first going to remember e to the x is equal to 1 plus x squared over 2 factorial, et cetera, which is the sum from n equals 0 to infinity of x to the n over n factorial. And then we're going to do two things. We're going to replace the x with an x cubed. So e to the x cubed is going to be 1 plus x cubed squared over 2 factorial plus x cubed over 3 factorial, et cetera, which is going to be the sum from n equals 0 to infinity of x cubed to the n over n factorial. And then we're going to multiply it by x squared. So x squared times e to the x cubed is just going to be x squared times all of that. And we can start simplifying things. That's x to the 6th over 2 factorial. That's x to the 9th over 3 factorial. And if we think about distributing that through, we have x squared plus x to the 5th plus x to the 8th over 2 factorial. We can see that the pattern, we're just really adding 2 to the power of x. Instead of getting x to the 3n, we're going to get x to the 3n plus 2 over n factorial. So that's the gist. And this is kind of a lot of the time how we want to, thank you, deal with Maclaurin or Taylor series of a function. You don't want to use the formula. Now, we're going to use the formula sometimes. Like sometimes you're just stuck with the formula because some functions are terrible. But if you see something, basically, if you see something from this list, if you see a 1 over 1 minus x, a 1 over 1 plus x, more generally, a 1 over 1 minus something, a sine of something, a cosine of something, a natural log of something, or even an inverse tangent. These are all series that you're kind of, I don't want to say expected to know because that's maybe a little too hard, but definitely like there are things you should recognize that you can manipulate easily. So just to kind of make this a little bit more exhaustive. And this is, these are all in, I think it's table 10.1 in section 10.10. These are listed. And most of them we know. We know, I feel like silly even writing them again because we've talked about them so many times, but really, really quickly, 1 over 1 minus x is the sum from n equals 0 to infinity of x to the n. And from there, you can know what 1 over 1 plus x is. 1 over 1 plus x is just 1 over 1 minus x, which is the sum from n equals 0 to infinity of minus x to the n. It's just the same thing, but alternating. And then the more general 1 over 1 minus some stuff, that's the one you really should think of, right? That's going to be 1 plus your stuff squared, et cetera, et cetera. I know it feels a little silly to write it that way, but that's really the one. This is the one, oops, that's an n. That's the one you're going to use like all the time, right? Like if you see 1 over 1 minus thing, that's what you're going to do. And then we have, of course, sine of x is the odd powers over their factorial. So it's x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. And cosine of x is, of course, the even powers. 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial. And then we have these last two. The natural log of 1 plus x, sorry, no, these last two that are up here. the natural log of 1 plus x, and the inverse tangent of x. So these are ones I'm often more likely to forget, to be honest. Natural log of 1 plus x, I don't remember, really. I remember that if you take its derivative, you get 1 over 1 minus x. Or 1 over 1 plus x, sorry. 1 over 1 minus x is what I was trying to say there. So the derivative of the natural log of 1 plus x is this. So the natural log of 1 plus x is the antiderivative of this. So the natural log of 1 plus x is x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4, et cetera, et cetera, et cetera. It's going to be the sum, welcome, thank you, from n equals 1 to infinity of x to the n over n times negative 1 to the n minus 1. I don't remember that one. Really, like I really was like, how do I get that? Oh yeah, it's just the antiderivative of that. And then we can do it there. And then finally, the inverse tangent one, welcome. The inverse tangent of x is the antiderivative of 1 over 1 plus x squared, which is the antiderivative of 1 over 1 minus x squared. So kind of the same idea. It's the antiderivative of 1 minus x squared plus x to the 4th minus x to the 6th plus x to the 8th, etc. And oh yeah, we can find that. That's going to be x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7, and so on. And as a formula, it would be x to the 2n plus 1 over 2n plus 1, and then alternating. So these are the ones you should kind of, I don't want to say know by heart, but yeah, fair enough. So I'll come back to that. Yeah, I really think you should know, like, oh, I forgot one of them, of course. Which one did I forget? We just used it. I'm missing a very important, there's definitely a formula of a Maclaurin series. I know you know it. It's not on this list. Yeah, thank you. We definitely should know e to the x is 1 plus x squared over 2 plus x cubed over 3 factorial plus x to the 4th over 4 factorial, etc., which is the sum x to the n over n factorial from n equals 0 to infinity. So this is a pretty comprehensive list of the ones you should know and the ones you should be able to manipulate. So like you could find sine of x squared or cosine of x cubed times x, or the natural log of 1 plus x cubed, right? All those you can just take the known formula and substitute in the part that you needed. Somebody asked the sums for sine, cosine, and natural log of 1 plus x. So natural log of 1 plus x is right there. But for sine and cosine, I didn't write them, it's fair. So for sine, we write it as the sum from n equals 0 to infinity of x to the 2n plus 1 over 2n plus 1 factorial times x to, negative 1 to the n. And for cosine, it's the sum from n equals 0 to infinity of x to the 2n over 2n factorial times the negative 1 to the n. Those are the formulas for those. But they're all, I think they're all, except for, I think all of them are in that table, except for the 1 over 1 minus stuff one. Yes, well, so because that's the oh, actually no, you're actually no, that should start at n equals 0. Thank you, and that should be a negative 1 to the n. Then sorry, apologies. It's really because I was looking at the other one. So I was looking at the natural log of 1 plus x1, which definitely does start at n equal to 1. He said not confidently at all. Yeah, that's right. Yeah. So if you're ever unsure, so like for the natural log of 1 plus x1, we could use Taylor's formula, right? We could start taking derivatives and plugging, and you can see that if you plugged in 0, right, for the first term, the function at 0 is equal to 0. So there shouldn't be a constant term out here. Yeah. So knowing these, we can do lots of weird things. Like, for example, I want to find the sum for, say, I should say find the Taylor series centered at 0. I should have just said Maclaurin series. For sine of x times cosine of x. Now, when you're multiplying them together, that's where things get a little crazy. So sine of x times cosine of x, yeesh. So I know sine is the odd ones, x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. And I know cosine is the even ones. That's looking kind of a little worrisome. Well, let's see what happens. So when you have to multiply them together, you just want to kind of group all the ones that have the same powers. So I see an x times a 1. Great. So that's going to give me an x. And there's no other terms that give me an x to the first. So then we'll look at the next possible highest power. It's going to be an x times an x squared over 2 and a 1 times the negative x cubed over 3. So my next term is going to be minus x squared over 2 factorial, x cubed, apologies, because it's x times x squared, minus x cubed over 3 factorial. And I'm going to have to put those together. And then I'm going to get, let's see, the next possible highest power I can get is an x to the 5th. So I'm going to have an x times an x to the 4th over 4 factorial. And then I should be writing little arrows here, right? See how this is getting really kind of gross? And then we're going to have this x cubed over 3 factorial times x squared over 2 factorial. So we're going to have a plus x to the 5th over 6 times 2. And then we're also going to have this plus x to the 5th over 5 factorial. Things are looking kind of weird. I don't want to do much more of this. So if we start just simplifying this, we're going to get an x minus, let's see, a negative 1/2 minus a 1/6 is going to be a minus 2/3. Okay, yeah, 3/6, what plus 1/6 is 4/6. 2/3 x cubed. And then, yeesh, 1 over 24 plus 1 over 12 plus 1 over 120. Luckily, I did the work already, and it's 2/15 x to the 5th. I'm not seeing a pattern real easily. Maybe there is one, but if there is, it's not really evident. Although I am noticing I'm only getting odd powers, which might make me think there's something to do with sine here. I mean, obviously there's something to do with sine because I'm multiplying by sine. So this is where knowledge of your trig identities is really maybe very helpful. So if I wander out the whole thing, well, I might remember that sine of 2x is equal to 2 times sine of x times cosine of x. And so if I wanted just sine of x times cosine of x, I could say that sine of x times cosine of x is equal to 1/2 times sine of 2x. And we know how to do that because we know sine of x, once again, is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, et cetera, et cetera, et cetera. So if I want 1/2 times sine of 2x, well, I'm going to take sine of 2x, which is going to be 2x minus 2x cubed over 3 factorial plus 2x to the 5th over 5 factorial, etc. And then multiply the whole thing by 1/2. And we can even write the formula for it, right? If I know that sine of x, the formula is the sum from n equals 0 to infinity of x to the 2n plus 1 over 2n plus 1 factorial times negative 1 to the n. I'm going to replace the x with a 2x. So I'm going to get the sum from n equals 0 to infinity of 2x to the 2n plus 1 over 2n plus 1 factorial times minus 1 to the n. And then I'm going to also multiply it by 1/2. That's it. Kind of cool. It's actually really cool. Like it's very kind of powerful, which is neat. And we can also, if we're really like concerned that we didn't do the right thing, we can check the first few terms. Right. So if I start actually simplifying this, my first term is x. My next term is, let's see, 2 cubed is 8, 8 over 2 is 4, 3 factorial is 6, 4 over 6, yeah, minus 4 over 6 x cubed, which is exactly what I had, except I didn't reduce 2/3 x cubed. If I check the next term, I'm going to get 2 to the 5th over 2 times 5 factorial times x to the 5th. And that's going to be 16 over 120, which is 8 over 60, which is 4 over 30, which is 2 over 15. So we don't need to do this checking, right? Like doing the process we've done is sufficient. But if you're worried, you can be like, well, let me check the first few terms just to make sure. And they do work out. So being able to kind of manipulate things in this way is, if you can, right? Like if you have a function and like find this function's Taylor polynomial or Maclaurin series, if you can do it this way, where you're just like getting to substitute things in, that is the way you should do it. Right? That's the better, easier way. But then, of course, sometimes there are functions that don't lend themselves so well to this. One kind in particular, which there is a formula for, but it's a little wonky. So let's talk about this next function. Let's say we have f of x equal to the square root of x, and we want to find the Taylor series centered at a equal to 9. Oops, sorry. This one is going to be a little bit strange. So again, we know our Taylor's formula. It's the sum from n equals 0 to infinity of the nth derivative evaluated at 9 in this case over n factorial times x minus 9 to the nth power. And so our job, which is sometimes hard, sometimes easier than it's going to be here, is to find a formula. So we want a formula for the nth derivative at a equal to 9. And this is where we just kind of have to start going. So our function is the square root of x, which you're almost always going to want to write as x to a power. And then we're going to start finding derivatives. Okay, so my first derivative is 1/2 times x to the negative 1/2. And my next derivative is going to be 1/2 times negative 1/2 times x to the minus 3/2. And my next derivative, so you really have to kind of do this for a little while to maybe see the pattern. So I'm going to get 1/2 times negative 1/2 times negative 3/2 times x to the negative 5/2. Let's do one more. The fourth derivative is going to be 1/2 times negative 1/2 times negative 3/2 times negative 5/2 times x to the negative 7/2. So I'm starting to see a pattern. I'm going to observe a few things. One, it's definitely oscillating. Well, it's definitely oscillating after the first term, right? Because it's positive, positive, and then negative, positive, negative, positive, negative, positive, negative, positive. So I'm going to have to adjust for that when I do it. Two, I can see that each subsequent term, I'm multiplying by another 2 in the denominator and by the next highest odd power in the numerator. Okay, so the way I can write this is, and so like just to kind of point out, right, I'm going to think of this as, actually not this one, sorry, this next one as like -1 times 1 over 2 squared times x to the negative 3/2. And this one is, yeah, -1 squared times 1 times 3 over 2 cubed times x to the negative 5/2. And this one here is a -1 cubed times 1 times 3 times 5 over 2 to the 4th times x to the negative 7/2. And the next one, just by kind of following the pattern, the next one would be -1 to the 4th times 1 times 3 times 5 times 7 over 2 to the 5th times x to the negative 9/2. So there's a couple ways you can write this. So I should say, right, essentially it looks like the last term of this product here is twice this number minus 3, right? And you get a 2m minus 3. So there's a couple ways you could write that. You could say that your nth derivative at x is going to be, well, let's see, it's going to be a -1 to the n minus 1 over a 2 to the n. And then we're going to multiply by a 1 times 3 times 5 times all the way up to 2n minus 3 times x to the negative. Ooh, that's the 9. So that number is 2 bigger than that. So that's a 2n minus 1 over 2. That's how I'm seeing it. I just kind of, now there is another way of writing this. No one else writes this in this other way. I mean, if you look at Grant's notes, he does talk about how you can write this. There is some weird, strange notation. I don't think anyone's going to talk about this, but just for your knowledge, it's kind of interesting. Another way of writing this is the double factorial notation. So here's what it is. N double factorial is equal to the product of all the odd terms if n is odd. So it's n times n minus 2 times n minus 4, all the way down to 5 times 3 times 1 if n is odd. And it's equal to the same thing all the way down to 6 times 4 times 2 if n is even. Kind of strange. So like if you really, really wanted to, instead of writing it like this, you could write this part here as 2n minus 3 double factorial. I don't recommend it, but in case it ever comes up, now you know what it is. If you ever see a double factorial, like, what are they doing? That's what they mean. So here's how we're going to write this. Oh, we still have one more part to do, right? We found the nth derivative at x, but now we have to plug in the 9, right? So our nth derivative at 9 is going to be -1 to the n minus 1 over 2 to the n times 1 times 3 times 5 all the way to 2n minus 3 times 9 to the negative 2n minus 1 over 2. That looks terrible. We can simplify this a tiny bit, like the fact that we have a 9 to the 1/2, which is just 3. So I'm going to rewrite this as -1 to the n times 1 times 3 times 5 all the way to 2n minus 3 over 3 to the 2n minus 1. That's a little better. Let me make sure everyone's okay with that. 9 to the negative 2n minus 1 over 2 is the same as 1 over 9 to the 2n minus 1 over 2, which is the same as 1 over 9 to the 1/2 to the 2n minus 1, which is 1 over 3 to the 2n minus 1. Probably not necessary, but fine. And then finally, we can write this as the square root of, wow, the square, all of this for the square root of x as a polynomial. The square root of x is equal to, now this is where we have to be a little bit careful. I don't want to start at n equals 0 because starting n equals 0 means I would have a product all the way to net, right? It's weird to start at n equals 0. We should really be starting at n equals 2, meaning we have to kind of adjust for the first couple terms. So if we look back here, right, I'm essentially going to get these first 2 terms by themselves, and then so those are our first 2 coefficients there. So we're going to get the following. We're going to have f of a plus f prime of a times x minus a plus f double prime of a times x minus a squared, 2 factorial, and so on and so on and so on. So looking at this horrible mess, our f of a was 3, our f prime of a was 1/6 times x minus a, which is 9. And then the rest of the terms we can get by throwing this formula at them. So it's going to be the sum from n equals 2 to infinity of, -1 to the n we'll see about that, times 1 times 3 times 5 all the way to 2n minus 3 over 3 to the 2n minus 1. There's also an n factorial that we need to throw in, right? Because it's your thing divided by n factorial. And then finally times x minus 9 to the n. That's a little bonkers. Now, I'm pretty sure that's wrong. And by wrong, I mean I need to fix it. Because if we think about what our terms were back in the beginning, it was going to be a, oops, sorry, you can't, I'm like showing you this thing like you can see it. We got a 3, and then the next term is going to be a 1/6 times, x minus 9. And then the next term, if I look at it, should be a negative number because it's a negative 1 times 1 over 2 squared. So what I actually probably need here is a n minus 1 is my power to fix the alternatingness. We could have maybe tried to start at n equals 1, but I feel like that would have been a little bit challenging. So this is a terrible formula, right? Like no one wants to do this. I certainly would never want to do this ever, really. But sometimes we need to. So the thing is, there are ways to make this less terrible. And the way of making this less terrible is to observe that, well, there's something called the binomial formula. So there is another thing. Of course, always off the page. So let's go very general, we'll kind of circle back around to that particular example. I want to write the first 5 terms for the very general Maclaurin series f of x equal to 1 plus x to the p, where p is any power, positive, negative. 0 would probably be weird, right? But whatever. So let's write it out the long way. F of x is going to be f of 0 plus f prime of 0 times x plus f double prime, right? This pattern comes up so many times. You really should just get used to being like, all right, here it is for this whateverth time. And this is all I'm really asking for, right? This is the first 5 terms. And then there would be more if you're actually finding it. All right, let's do it. So we know that f of x is 1 plus x to the p. F prime of x is p times 1 plus x to the p minus 1. F double prime of x is p times p minus 1 times 1 plus x to the p minus 2. F triple prime of x is going to be p times p minus 1 times p minus 2 times 1 plus x to the p minus 3. And we're definitely starting to see the semblance of a pattern. I'll be real honest. I usually have to write out at least 3 or 4 terms to even have a shot at seeing the pattern, right? Like it's hard to see these patterns sometimes. So if we plug in 0, f of 0 is going to be 1, or 1 to the p, which is 1. We plug in f prime of 0 is going to be p times 1. F double prime of 0 is going to be p times p minus 1 times 1. F triple prime of 0 is going to be p times p minus 1 times p minus 2. The fourth derivative of f at 0 is going to be p times p minus 1 times p minus 2 times p minus 3. So I think we can write out the formula here. I suppose if I was being honest about the problem, we should answer the question and then do the long version. So the first 5 terms are going to end up being, well, let's see, I'm just going to throw it into the formula here. So I'm going to get 1 plus p times x plus p times p minus 1 times x squared over 2 factorial plus p times p minus 1 times p minus 2 over 3 factorial times x cubed plus p times p minus 1 times p minus 2 times p minus 3. You're going to fit over 4 yeah, that's right. Sorry. Yeah. over 4 factorial times x to the 4th. Barely. Okay. This definitely suggests a pattern. The pattern being, so the Maclaurin series for 1 plus x to the p is given by, the following pattern. I'm just going to write dot, dot, dots at the end. 1 plus x to the p is equal to 1 plus p times x plus b times p minus 1 over 2 factorial times x squared plus dot, dot, dot. There is a way you can write this. It's kind of annoying, but you can write it as the sum. Actually, let me make sure yeah. Yeah, this is the, no. You could write it as a sum. It's better just write it this way. There is a formula, but it's not any nicer than just knowing what this is. So yeah, I don't even want to do that. So the interesting thing about this is that it works for any power, meaning it works for positive and negative and fractional powers. So for example, we could say, all right, I want the Maclaurin series for the square root of 1 plus x squared, or 1 plus x squared to the 1/2 power. All right, so let's see. That's going to be, well, I'm just using this pattern. I'm replacing the x with x squared. I'm replacing the p with 1/2. So 1 plus x squared to the 1/2 is going to be, let's be very specific here. That's replacing x, that's my p. So it's going to look like this. It's going to be 1 plus 1/2 times x squared plus, now things get kind of weird, 1/2 times negative 1/2 over 2 factorial times x squared squared plus 1/2 times negative 1/2 times negative 3, right? It's that same pattern we were seeing in the previous problem. Which, again, you might feel like we need to find the formula here. I might feel like we need to find the formula here, but that's not essentially the point. The point is that we can kind of do this thing and see this thing and not have to find a formula for it necessarily. You could find a formula, but it's, I say you could. We definitely could. I really don't think we want to spend our time doing that unless you really want me to. We can do it, but it's kind of gross. What we can do with this is not have to, let me change it. So let's say we wanted to use the first 4 terms of the binomial series for f of x equal to the square root of 1 plus x cubed to estimate this integral. Why would you maybe want to do that? Because that thing can't be integrated. So this is actually a plausible application of Maclaurin series, right? There are functions, lots of them, that can't be anti-differentiated. But if we want to approximate the area under their curve, we can use their Taylor series or the Maclaurin series to get a good estimate for them. So this here is a, let's see, I know that 1 plus x to the 1/2 is 1 plus 1/2 x plus 1/2 times 1/2 minus 1 times x squared over 2 factorial plus 1/2 times 1/2 minus 1 times 1/2 minus 2 over 3 factorial times x cubed. But then I'm going to plop in the x cubed for x. So 1 plus x cubed to the 1/2 is going to be 1 plus 1/2 x cubed plus, I might as well do a little simplifying along the way here. 1/2 times negative 1/2 divided by 2 is going to be a negative 1/8 times x cubed squared is going to be x to the 6th. And then let's see, this one's a little grosser here. 1/2 times negative 1/2 times negative 3/2 is going to be negative 3/8 divided by 6 is going to be a negative 1/16. So that's positive, sorry, positive 1/16. X cubed is x to the 9th. So there is my, now I should point out, this is not the 4th order Maclaurin series. This is the Maclaurin series, the first 4 terms in the Maclaurin series. So don't confuse the word terms with the word order. Order, the easiest way I've been able to make order make sense in my head is the order of a series is the highest power you're allowed to write down. So if they say order 4, we would write 1 plus 1/2 x cubed. And stop there. You've exhausted your powers. This would be, I guess, a 9th order Maclaurin series for this particular polynomial, for this particular function. So then we want to use the first 4 terms to estimate the integral. So we're going to say, well, the integral from 0 to 1 of the square root of 1 plus x cubed dx is going to be approximated by the integral from 0 to 1 of this lovely polynomial. 1 plus 1/2 x cubed minus 1/8 x to the 6th plus 1/16 x to the 9th. And then we do the usual thing. We anti-differentiate. We get x minus, plus x to the 4th over 2 times 4 minus x to the 7th over 8 times 7 plus x to the 10th over 16 times 10 from 0 to 1. Good times. So that's going to equal 1 plus 1/8 minus 1/56 plus 1 over 160. Which we definitely should not simplify that fraction. Unless you have nothing better to do with your time. But on a test, definitely not, right? Leave it like that. Question. What's the largest possible error of this estimate? Well, is this thing alternating? That's a bad question. The answer technically, I guess, you could make an argument for the answer is no, because technically the first 2 terms are the same sign. But after the first term, is it alternating? Yes. And if a series is alternating, then the error is at most the absolute value of the next term. So the next term, right? The next term, okay, the next term, let's see, the next term would have been, 1/2 times negative 1/2 times negative 3/2 times negative 5/2 over 4 factorial times x to the 3rd to the 4th, which is x to the 12th. Okay, it's real dicey there. We can do it. So let's see, that's 1 times 3 times 5. That's going to be a 15. It's going to be negative over 16 times 24. And then we would anti-differentiate that. So if we had grabbed the next term, right, the next term would have been an x to the 13th over 13 times this terrible coefficient. And so the largest possible error in our estimate would have been 1/13 times 15 over 16 times 24. I dropped the negative because I would take the absolute value. Not nice, but certainly something we can find. So this all feels very messy, right? Like it's just a lot of like little pieces here and there, details. It gets kind of, I don't know. I feel like it's very nitty gritty. Like it's hard to feel like you're having a good time doing this math. Because it feels like, all right, there's a bunch of these details, I have to pay attention to them. Let's continue in that vein for one like a little bit longer, and then we'll do something a little more interesting, I promise. All right, so sometimes you want to estimate a thing and you want to know how big your error is, and the thing isn't alternating. So most of the time you've been asked to say, like, how big can the error be? We've been looking at an alternating series, but that's not always the case. So just as a reminder, So we're going to look at Taylor's remainder theorem. And so first, I'll just say the thing I said before. If we have a decreasing alternating series, it needs to be decreasing so that the series is convergent in the first place. But if we have a decreasing alternating series, the error is always bounded by the next term. So for example, the error Rn is always less than or equal to the absolute value of whatever the next term is. So another example of this, sine x equal to x minus x cubed over 3 factorial, etc. We could approximate sine of 1. I don't know what sine of 1 is. I can say that sine of 1 is approximately 1 minus 1 over 3 factorial plus 1 over 5 factorial. And if I stopped there, I could say that the maximum error is going to be the absolute value of the next term, which is negative 1 over 7 factorial, which is just 1 over 7 factorial. That's a pretty good estimate, right? 7 factorial is, I don't know, it's a largest number. I mean, okay, it's like 5,000-ish, close to 5,000, right? That's a pretty good estimate. But if the series is not alternating, we can't use this. How do we estimate error? Well, there's a formula. There's Taylor's remainder theorem, which says that the error after you sum the first n terms, the remainder after those first n terms is less than or equal to the absolute value of the n plus 1 derivative of your function, evaluated some z, we'll talk about z in a second, times x minus a to the n plus 1 over n plus 1 factorial. Which is a lot more complicated, right? Don't you wish we could just be like, it's the next term? That's why we usually ask about alternating things. But if you don't have alternating, this is what you do. And there's a couple of restrictions here. So fn plus 1, the nth derivative of f at z, is the maximum value of the n plus 1 derivative of f, where z is between x and a. It's kind of a lot. It could be worse. Let's look at an example to help kind of clarify what we're doing here. So let's use a third degree Taylor polynomial to approximate e to the 1, which is just e, and put an upper bound on the error. It might feel kind of silly to approximate e because like we know e is like 2.71828, so on. But it's more illustrative if we use something we know. So we know the Taylor polynomial, I should say Maclaurin polynomial for e to the x. It's 1 plus x squared over 2 factorial plus x cubed over 3 factorial. There's my third degree Taylor polynomial. So then we're going to say that e to the first power is approximately 1 plus 1 plus 1/2 plus 1/6, which is equal to 2 plus 3, 4, 6, 2 2/3, which is 8/3, or 2.6666 forever, if you like. Not all that great an estimate, right? We know the polynomial or the value of that thing better just on our own, right? I know it's like 2.71. It's a better estimate than 2.6666. Fine. But now let's talk about the error. So the remainder has to be less than or equal to the absolute value of the fourth derivative, or actually the 1, 2, sorry. So this is where, so this way, this is n equals 0, yeah, n equals 1, n equals 2, n equals 3, of the fourth derivative of our function evaluated at z. Our x value, well, we're plugging in 1. That is your x value. What's our a value? Where did I center this thing at? Well, if it was centered at 2, it looked like, you know, x minus 2, x minus 2 squared, x minus 2 cubed. So if I don't have an x minus something, where did I center it at? Centered at 0. And maybe I should have used the word Maclaurin to make it more obvious that, oh yeah, we're centered at 0. But the way this is written, this should be fairly clear that this is centered at 0. 1 minus 0, it doesn't really matter that it should be to the n plus 1 power, but I'm going to put it there anyway. So that should be 3 plus 1 over 3 plus 1 factorial. So I should point out, it's kind of like the next term in the Taylor polynomial, the Maclaurin series, the Taylor series, except that it's not the nth derivative evaluated at 0 or whatever your center is. It's the nth derivative evaluated at the place that makes it as big as possible. So our fourth derivative, well, fortunately, our function is e to the x. Our fourth derivative is e to the x. Right? We know the derivatives of e to the x are always just e to the x, e to the x. So now the question is, what value maximizes e to the x on the interval from 0 to 1? Because that's where I'm working with. I'm between my center and my x value. Okay, well, e to the x is an increasing function, right? E to the x looks like that. So what value of x am I going to plug in that's going to make it the biggest? I know you all want to say it. No, nobody wants to say it. Okay, so I'm going to pick 0, right? Plug in 0. I'm not going to pick 0. But I am because you guys didn't say anything. I'm going to pick 1. Because if I plug in 1, that's going to make this function the biggest. So I'm trying to maximize this fourth derivative. Now, here's the problem with picking 1. I pick 1, my fourth derivative is e. And it feels kind of silly or maybe wrong to say, okay, I'm approximating e, and then I want to talk about my error, and I'm going to use the exact value of e to talk about my error. It just feels kind of like cheating. So what we often do when one of these values is something that like doesn't feel like something we should technically know, because we're kind of trying to approximate that thing in the first place, is to say, well, this is certainly equal to e times 1 over 4 factorial. And then we kind of just round up our irrational thing to the next whole number. So I would say, well, that's definitely less than or equal to 3 times 1 over 4 factorial, which is 3 over 24, which is 1/8, which is 0.125. So the reason we do this is just to get a better kind of answer, right? It feels weird to say my error is at most e over 24. But it's certainly true. If this is an upper bound, then this larger number is also an upper bound. So it's usually okay to increase how much your error is, right? If you're saying my error is at most this, you can say, well, I can make it a little bit bigger, and that's still true. It's at most this. It's not actually ever going to be this large, but we're just trying to get an upper bound on how large it can be. All right. Let's see, what time is it? Okay. We'll come back to you. Yeah. All right, let's. Yeah, there was one other problem I saw too. It was really cool. Oh, yeah, we'll do that one, sure. Here's something that sometimes people skip, but it's kind of like, why would you skip the coolest thing you can talk about? Euler's identity. His name is pronounced Euler. A lot of people say Euler, but it's Euler. So a couple things we need to know for this. So actually this is how we're going to relate sine and cosine and e to the x all in one nice equation. It's kind of cool. If you haven't seen this before, it's so cool. So remember this number I, that's the square root of the -1. We're going to use that. So then what's I squared? -1. And I cubed is, I cubed. So here's what I would do. I would say I cubed is I squared times I, which is -1 times I. So it's negative I. And then I to the fourth is I squared times I squared, which is -1 times -1, which is 1. And then I to the fifth is going to be I to the fourth times I, which is 1 times I, which is I. So we got this kind of cycle. In fact, when I think about this cycle of powers of I also kind of, not actually very relatedly, think about the cycle of the derivatives of sine and cosine. Right? Sine and cosine, if you take their derivatives, it's a cycle of 4 iterations, right? Derivative of sine is cosine, derivative of cosine is negative sine, derivative of negative sine is negative cosine, derivative of negative cosine gets you back to sine. So if you do this thing 4 times, you get back to where you started. The same thing is true here. If you multiply I by itself 4 times, you get back to where you started. So I times I is -1, times another I is negative I, times another I is +1, times another I, you're back to I. So it keeps going, right? I to the 6th is going to be -1, I to the 7th is going to be negative I to the 8th is going to be 1. Boom, you're back to where you started. All right. So then we're going to take our formula for e to the x, which is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial, and so on and so on and so on. By the way, just to point out, sometimes I write 2, sometimes I write 2 factorial. I write 2 because I'm lazy, because 2 factorial is 2. So don't ever think there shouldn't be, like, there is a factorial there. If I don't write it, just it's equal to 2. So that, if you were wondering, that's what's happening. And then we're going to replace x with I times, instead of x, we're going to use theta because, well, we're going to have trig functions come up. So it's nice to use an angle name instead of something else. So let's see what we get. We get 1 plus, I'm replacing x with I times theta. Replacing x squared with I times theta squared, 2 factorial, plus I times theta cubed over 3 factorial, and so on. Okay. So now we're going to simplify this a little bit. And we're going to use the fact that I to a certain power gets you a certain thing. So we're going to get 1 plus I times theta. I squared is -1. I cubed is negative I times theta cubed over 3 factorial. I to the 4th gets you back to 1. I to the 5th is going to be just I. I to the 6th would be -1. And so on and so on and so on. Okay, so now we're going to group together the terms that have i's and the terms that don't. Sounds like we're saying like things with i's and the things without i's. We're not, we're I the letter. So these terms, red pen. All those terms, all the terms that have an odd power of theta are going to have an I in them. And all the terms with an even power of theta don't. So we're going to write this as 1 minus theta squared over 2 factorial plus theta to the 4th over 4 factorial minus theta to the 6th over 6 factorial plus so on and so on and so on. Plus, I'm going to factor out the I from these other terms and have I times a theta minus a theta cubed over 3 factorial plus a theta to the 5th over 5 factorial. There would be a minus theta to the 7th over 7 factorial. Those look awfully familiar. That looks a lot like the Maclaurin series for what? Right. This is exactly cosine of theta And this is exactly I times sine of theta. So Euler's formula says e to the I theta is equal to cosine theta plus I sine of theta. This is actually a really important formula when you talk about analyzing systems of linear differential equations. This comes up when you talk about like the behavior, the stability or instability of your equilibria, which I know is not what this class is about, but if you probably will all take 22B, most of you, I'm sure, are on the path of eventually taking that. This formula definitely is featured heavily in that class. There's also a kind of cool fact. Fact is maybe no fact. This formula leads to what's considered one of the most beautiful formulas in math. I don't know if I really agree, but it's a cool formula because it gives you all 5 of like the most important numbers. You've probably heard of it before. I would start it this way: e to the I pi equals cosine of pi plus I times sine of pi. So e to the I pi equals cosine of pi is -1, sine of pi is 0. And then people often write this as e to the I pi plus 1 equals 0. An equation involving 5 of math's most important constants: e, I, pi, 1, and 0. It's neat. It's not particularly important, but it's neat. So there are some things that are interesting about this that are worthwhile. Like, for example, check this out for a second. What if I did e to the I times 2 theta, which you could also think of as e to the I theta squared? Oops, you might want to see the things. You all are always welcome to say, James, I cannot see what you're writing, or it looks really dumb because you have that paper angled. Let's look at both sides of this. So I'm going to use my formula. Oh, I forgot what the formula was already. E to the I theta equals cosine theta plus I sine theta. So really, I'm thinking of this as e to the I times 2 theta. No, why am I rewriting? This is going to be cosine of 2 theta plus I sine of 2 theta. And it's going to equal cosine of theta plus I sine of theta squared, which I should multiply out. That's going to be cosine squared theta plus 2 sine theta cosine theta times I plus I sine theta quantity squared is going to be I squared sine theta, sine squared theta. But what's I squared equal to? You guys were like, you know, okay, fine. I squared is -1. Okay, so check this out. When you have imaginary numbers equal to each other, if they are equal to each other, the real parts have to equal to each other and the imaginary parts have to equal to each other. So this imaginary part here has to equal this imaginary part here. So it is definitely true that I times sine of 2 theta is equal to I times 2 times sine of theta times cosine theta. Or ignoring the imaginary parts or canceling them out. Oh, look, there's a trig identity that we know. Sine 2 theta is equal to 2 sine theta cosine theta. And you also get the other one for cosine. Cosine 2 theta is exactly equal to the real parts of this, which is cosine squared theta minus sine squared theta. So again, kind of neat. There's some things that really do show up here that may be surprising, definitely interesting. So where'd you go? I had a thing. Sorry, one sec. So many papers. I'm always using stuff. Oh yeah, there we are. So that was kind of fun. And it does come up on occasion. There are definitely problems where this particular formula is actually used. But let's go back and spend our last 10 or 15 minutes here doing a couple more things. So let's try it out. I saw this problem in your homework or someone's homework, and I thought it was a good problem. So let's find the Taylor polynomial for f of x equal to 1 over 4 minus x to the 5th at a equal to 3. Centered at a equal to 3, if you like. Okay, so and that is a 5, not a 3. And then my 5s look like 3s. How would I start approaching this problem? I don't see what I want. I mean, I kind of see what I want. I see a 1 over something minus x, but it's raised to a 5th power. If I really, really tried, I could probably do a bunch of antiderivatives and get back to like a 1 over something minus x, but it seems dicey. I would probably start just taking derivatives. Also, here's a good clue that we should start taking derivatives. If I plug in 3, I'm going to get a 1 to a power. That's usually a good sign that plugging in the number to your derivatives is not going to be terrible. It's going to be moderately okay. So let's start taking derivatives and see what happens. So our function is 4 minus x to the negative 5th. Our first derivative is going to be, again, we're going to see this thing where we get the negative power coming down, but we also multiply by a -1 because of the chain rule. So I'm just going to say that's going to be 5 times 4 minus x to the negative 6. Because it's a -5 times 4 minus x to the negative 6 times -1. And then my second derivative is going to be 6 times 5 times 4 minus x to the -7. We should definitely not simplify, right? We want to see the pattern of writing the numbers out. 7 times 6 times 5 times 4 minus x to the -8. I think interesting. Yeah. So I'm going to talk about another way of doing this because I just thought of another way of doing this, but let's see this first. So the fourth derivative is going to be 8 times 7 times 6 times 5 times 4 minus x to the -9, and so on and so on and so on. So it looks like if I want to take the nth derivative, I'm going to get essentially, well, let's see. It looks like I'm always starting at a number that's 4 bigger than whatever derivative I'm taking, right? I'm at the fourth derivative, I got 8, third derivative 7. So it looks like I'm going to want n plus 4 times n plus 3 times all the way down to, I have to stop at 5. And maybe it's not going to work for this first term. We'll see. And then I'm going to have a 4 minus x to the number that's 1 larger than whatever that one is there. So it's going to be a n plus 5, but it's a negative n plus 5. That part's not really going to matter though, because we're going to plug in 3. So I can see that f of 3 is going to be 1. And f prime of 3 is going to be 5. And f double prime of 3 is going to be 6 times 5. And f triple prime of 3 is going to be 7 times 6 times 5, and so on. So I forgot the 7 there. And so it looks like the nth derivative at 3 is going to be n plus 4 times n plus 3 all the way down to 6 times 5. Which, if you wanted to make that a little more compact, you could write this as n plus 4 factorial over 4 factorial. All right, I want all the terms n plus 4, n plus 3, n plus 2, all the way down to 3 times 2 times 1, but I actually don't want the 4 times 3 times 2 times 1. So I canceled out with the 4 factorial there. That would totally work for all these terms except for the first one, which okay. Oh yeah, no, that'll work for the first one too, right? If we plug, so this would be n equals 1 we would get a 1 plus 4, so 5 factorial over 4 factorial, which would be 5. And if we plug in n equals 0, 4 factorial over 4 factorial is going to give us a 1. So it'll totally work for all of them. Great, that's even better. So then we should be able to write our formula as the sum from n equals 0 to infinity of this here, n plus 4 factorial over 4 factorial over n factorial, which instead of like doing a fraction and a fraction, let's just be smart about it, times x minus 3 to the nth power. So that seems right to me. We might want to check just to be sure. If I plug in 0, oh yeah, if I plug in 0, I'm going to get 1 times x minus 3 to the 0. If I plug in 1, I'm going to get 5 factorial over 1 factorial times 4 factorial. I'm going to get 5 times x minus 3 to the first. So yeah, it looks like this is the right way to do it. I will mention, you could have done this using the binomial formula. It didn't occur to me at first when I saw it. So again, that binomial formula, which is kind of a weird formula, which is that, honestly, sorry, which is this formula here, which is that 1 plus x to the p is equal to, oh man, I always forget the terms of this. 1 plus p times x plus p times p minus 1 over 2 factorial times x squared, and so on. Sorry, I got a little carried away there. Apologies. Wow, James. Hold it to, wow, let me just try that again. Sorry. So the reason I want to mention this is because it might be easier to get there this way. But you might be thinking, well, James, our thing was centered at 0 or at 3, and this thing is centered at 0. Well, we can fix it. So you could have written 1 over 4 minus x to the 5th as 4 minus x to the negative 5th. And here's the part where it's a little weird, as 1 plus 3 minus x to the negative 5th. So this thing is acting like your p, or sorry, like your x. And so if I start writing this out, my 1 plus x to the p is going to be 1 plus negative 5 times 3 minus x plus negative 5 times negative 6 over 2 factorial times 3 minus x squared plus negative 5 times negative 6 times negative 7 over 3 factorial times 3 minus x cubed. To me, this doesn't look better, but if you worked a little, we could manipulate it and say, so this is where I'm going to be switching things around a little. This is going to be 1 plus 5 times x minus 3 plus 6 times 5 over 2 factorial times x minus 3 squared plus 7 times 6 times 5 over 3 factorial times x minus 3 cubed. How am I switching things like that? Well, what I'm essentially doing is I'm saying I can take the negatives from here and multiply them over here. So really I'm thinking of this as a negative 1 times 3 minus x, which is an x minus 3. And here I have a negative 1 times a 3 minus x and a negative 1 times a 3 minus x, which is an x minus 3 times an x minus 3. And then this is looking a lot like what we just had. We could totally write this as the sum from n equals 0 to infinity of, I'm going to have an n plus 4 factorial over n factorial times 4 factorial times x minus 3 to the n. It's kind of neat. So the binomial formula, to me, it always feels like, I don't want to have to use it, but sometimes you kind of have to use it. But it is probably worthwhile to memorize. Or memorize, you should definitely be aware of it, is what I would say about the binomial formula. It can come up Oftentimes you can brute force figuring out the formula for it, but it's a little dicey sometimes. I think there was one other one I saw that really looked like I want to mention to you all. Oh yeah, this one. Okay. Yeah. So this problem that's phrased in two ways. So use a Taylor series, to find the following Taylor series: f of x equal to 1 over, let me change it a little bit, 9 minus x centered at x equal to 8. So if I want to center this at x equals 8, I would really like there to be an x minus 8 in there. Also, I'd really like to have a 1 over 1 minus something. But those are both going to give me exactly what I want. I can write this as 1 over 1 minus x minus 8. Sneaky, right? It feels very sneaky, like I'm just cheating completely. I'm not, but it feels like I am. If you're not sure how to, so really what I should have done though, is I should have said, I really want 9 minus x to equal 1 minus something. Let's call it y. And then you can solve for y. So subtract 1 from both sides. Multiply both sides by -1. Oh yeah, 9 minus x is 1 minus 8 minus x. Or sorry, x minus 8, apologies. Exactly what I want. And then that's going to be your usual geometric series. 1 plus x minus 8 plus x minus 8 squared plus x minus 8 cubed, and so on. The sum from n equals 0 to infinity of x minus 8. But then the next question that's almost exactly the same, but not. Now find the function 1 over 9 minus x centered at, I should have said a, but they say x. So now I want to center it at 0. Indeed. So the trick for doing one like this, I still want it to look like 1 over 1 minus something. The something I want though is something that when I plug in 0, I get 0. The something I want here is something that when I plug in 8, you get 0 in that part. Basically, I think of the center as being like if you plug that number in, the thing that's you're looking at is going to be 0. Right, that thing there should be 0. So here I really want like 1 over 1 minus, I would like 1 over 1 minus x, but I can't have it. So I factor out the 9 from the denominator. And then I'm going to have 1/9 times 1 over 1 minus x over 9, which the 1 over 1 minus your stuff is exactly 1 plus x over 9 plus x over 9 squared plus x over 9 cubed, and so on and so on and so on. So we could write this as the sum from n equals 0 to infinity of x over 9 to the nth power times a 1/9. And then if you want to write it out a little more simplified, you can write it as x to the n over 9 to the n plus 1. So, question. Which of these is the better one? Well, that's not a very good question. Why would one of them be better than the other one? Well, let me ask you a different question. Which of these converges for more values of x? What's the radius of convergence here? Well, we know that for a geometric series, the ratio has to be between -1 and 1. So here x is between 9 and 7, and our radius is 1. Here, on the other hand, we still have to converge when our ratio is between -1 and 1. But look, this gives a much larger interval and radius of convergence. In fact, this radius or interval of convergence completely encompasses this radius interval of convergence. So if someone were to ask which of these was better, this is the better way of doing it because it has a larger interval of convergence. It's kind of interesting. Definitely you can do it either way, but this is kind of the preferred way. Again, assuming that we didn't care where it was centered at. If you care where it's centered, then you obviously have to pick one over the other. But if someone said just like find a series for this function and they didn't tell you where to center it, typically centering it at 0 is the choice that gives you kind of the biggest interval of convergence.